Today, we're not venturing into the distant reaches of space. Instead, we're embarking on an equally extraordinary journey, one that takes us through the past, present, and future of our own planet Earth. Beneath your feet at this very moment, colossal forces are at work. Continents drift across the globe at speeds measured in centimeters per year. Deep underground, rock flows like thick honey under immense pressure. And at Earth's core, a churning mass of molten iron generates the magnetic shield that protects all life from deadly cosmic radiation. This is the story of plate tectonics, the geological engine that has shaped our world for billions of years and will continue sculpting it for billions more. We'll explore what forces drive the continents to wander across the planet's surface, why mountains rise and oceans open, and where our land masses are heading in the future. Along the way, we'll descend into Earth's deepest layers, uncover ancient life preserved in extreme conditions, decode the mysteries of global climate patterns, and even imagine an alternate Earth where dinosaurs never went extinct. Welcome to a journey through deep time and deep space, the inner space of our remarkable planet. Our planet is covered with vast oceans and sprawling continents. Towering mountain ranges, deep ocean trenches, and active volcanoes dot its surface, all consequences of Earth's dynamic, tectonic, and magmatic life. But to truly understand these surface features, we must peer deep into Earth's interior. The problem? We can't simply drill down and take a look. The deepest mine on Earth reaches just 4 kilometers into the crust. The Kola Super Deep borehole in Russia's Kola Peninsula achieved a record depth of 12,262 meters, about 7.6 miles, making it the deepest hole ever drilled by humans. Yet even this impressive feat penetrated only about 1/3 of the way through the continental crust, which ranges from 30 to 40 kilometers thick. That's a mere 0.2% of the distance to Earth's center. Despite these limitations, scientists have developed ingenious methods to study our planet's interior. Seismic surveys measure vibrations from earthquakes or artificial explosions traveling through Earth. Different materials transmit these waves at different speeds, allowing researchers to map internal structures without ever seeing them directly. Gravitational measurements detect variations in Earth's gravitational field caused by density differences in subsurface rocks. Deep drilling extracts core samples from boreholes, providing direct physical evidence of rock composition and temperature. Paleomagnetic studies examine the orientation of magnetized crystals in rock layers, revealing how continents have moved over geological time. Meteorite analysis offers clues about Earth's composition, since our planet likely formed from similar material as these space rocks. Laboratory modeling recreates extreme conditions of pressure and temperature to understand how materials behave deep underground. Paleontological surveys study fossilized remains that provide information about ancient environments and geological processes. Through these methods, scientists have determined that Earth has a layered structure resembling a cosmic onion. The crust forms the thin, outermost shell, Earth's skin, if you will. It's the thinnest major layer, but the only one we can directly observe and study. The mantle comprises 70 to 80% of Earth's volume. Composed primarily of solid rock, it extends from the base of the crust down about 2,900 kilometers. Temperatures range from approximately 1,000 degrees Celsius near the crust to 3,700 degrees at its deepest extent. While mostly solid, the mantle contains a partially molten layer that allows material to flow very slowly over millions of years. The core makes up roughly 30% of Earth's mass. The outer core consists of liquid iron and nickel, while the inner core is solid despite temperatures reaching 4,400 to 6,000 degrees Celsius. The extreme pressure at Earth's center prevents the inner core from melting. The interaction between the liquid outer core and solid inner core generates our planet's protective magnetic field. For understanding plate tectonics, the most important concept is the lithosphere, Earth's rigid outer shell comprising the crust and uppermost solid mantle. The lithosphere floats atop the asthenosphere, a more ductile, partially molten layer that allows the overlying plates to glide across Earth's surface. Think of it this way. The lithosphere consists of broken pieces, like a cracked eggshell, with each piece representing a tectonic plate. The major plates include the Pacific, North American, South American, Eurasian, African, Antarctic, and Australian plates, along with numerous smaller ones. Earth's entire topography, the arrangement of continents, the depth of ocean basins, the height of mountains, results from the movement and interaction of these lithospheric plates. For centuries, philosophers and scholars puzzled over Earth's geological features. Ancient Greek and Eastern thinkers proposed various theories about how mountains formed and landscapes changed. During the Middle Ages, the prevailing theory suggested that as Earth cooled, it contracted like a drying apple, causing the crust to wrinkle and form mountains. While creative, this explanation proved inadequate. The breakthrough came in the early 20th century from an unlikely source, Alfred Wegener, a German geophysicist and meteorologist. In 1912, Wegener proposed that approximately 200 million years ago, all continents were joined in a single massive supercontinent he named Pangaea, Greek for all Earth. Wegener's theory rested on several compelling observations. The coastlines of Africa and South America fit together like puzzle pieces. Identical fossil species appeared on continents now separated by thousands of kilometers of ocean. Similar rock formations and mountain ranges aligned across different continents. Evidence of ancient glaciation appeared in now tropical regions. Wegener envisioned Pangaea divided into two major landmasses, Laurasia in the north and Gondwana in the south, separated by the Tethys Ocean. He proposed that these continents gradually drifted apart to their current positions. Despite the evidence, Wegener's theory faced fierce opposition. Critics demanded an explanation for how continents could plow through solid oceanic crust. Without a mechanism, continental drift remained controversial until Wegener's death in 1930. The theory gained new life in the 1950s and 1960s through three critical developments. Geophysical exploration with advanced instruments allowed comprehensive mapping of Earth's structure across vast regions. Aerospace technology provided satellite imagery that revealed patterns in mountain ranges, fault lines, and geological structures never before visible. Ocean floor mapping proved most revolutionary. Using sonar technology developed during World War II, scientists discovered a massive system of mid-ocean ridges, underwater mountain chains stretching 65,000 kilometers around the globe. They also found deep ocean trenches, transform faults, and volcanic zones forming a connected network of geological activity. Crucially, researchers discovered that ocean crust is much younger than continental crust. While the oldest continental rocks date back 3.5 billion years, the oldest ocean floor rocks are merely 170 to 200 million years old. Furthermore, the seafloor grows progressively older, moving away from mid-ocean ridges toward continental margins. This observation led to the theory of seafloor spreading. New oceanic crust forms at mid-ocean ridges as magma rises from the mantle, solidifies, and pushes existing crust aside like a conveyor belt. This mechanism finally explained how continents could move. They don't plow through oceanic crust. Rather, both continents and ocean floors ride atop moving lithospheric plates. When scientists mapped global earthquake activity, they discovered that seismic events don't occur randomly. Instead, earthquakes concentrate in narrow, elongated zones that often coincide with dramatic topographic features like mountain ranges and ocean trenches. These zones mark the boundaries where tectonic plates interact. The modern theory of plate tectonics was born. Plate boundaries fall into three categories based on their motion. At divergent boundaries, plates move apart from each other. As they separate, the lithosphere thins and molten mantle material rises to fill the gap. This process creates deep rifts or rift valleys. Examples include the Baikal Rift in Siberia and the East African Rift System, which stretches several thousand kilometers. As rifting continues, the lithosphere becomes thinner, the mantle rises due to thermal expansion, and the surface elevates to form highlands or plateaus. Eventually, continued rifting can split a continent entirely, allowing seawater to flood in and create a new ocean basin. The Red Sea represents this process in action. It's a young ocean born from the rifting between Africa and the Arabian Peninsula. The Red Sea widens by about 1 meter per century as Africa moves northeast at nearly 2 centimeters per year. In simple terms, divergent boundaries increase Earth's surface area by creating new crust. If Earth's surface area increases at divergent boundaries, there must be zones where it decreases to maintain balance. This occurs at convergent boundaries where plates collide. When an oceanic plate meets a continental plate, the denser oceanic plate dives beneath the lighter continental plate in a process called subduction. The Pacific plate, for example, moves northwest at 8 centimeters per year and collides with the Eurasian plate. The heavier Pacific crust subducts beneath Eurasia, creating deep ocean trenches and chains of volcanoes. Subduction zones are geological recycling centers. The descending oceanic crust can drag down pieces of continental material, which melts at depth. Because this material has lower density than the surrounding mantle, it rises back into the crust, often erupting as volcanoes. This is how many of Earth's volcanic arcs formed. When two oceanic plates collide, the older, colder, denser plate typically subducts beneath the younger one, forming an island arc volcanic chain above the subduction zone. When two continental plates collide, neither can subduct because both are too buoyant. Instead, they crumple together in a process called collision, creating massive fold mountain ranges. The Himalayas exemplify this process. They formed from India's collision with Asia as India moved northeast at 5 centimeters per year. The entire alpine Himalayan mountain belt represents the wrinkled face of an aging planet. These mountains result from Africa's northeastward movement at 2 centimeters per year, India's northeastern drift at 5 centimeters per year, and Arabia's northeastern motion at 2.7 centimeters per year. This differential movement created the Red Sea and dooms the Mediterranean Sea to eventual closure. In approximately 50 million years, Africa's continued northward push will eliminate the Mediterranean entirely, replacing it with a mountain range rivaling the Himalayas. Earth will be truly unrecognizable. At transform boundaries, plates slide horizontally past each other at different velocities. In ocean basins, transform faults cut perpendicularly across mid-ocean ridges, segmenting them into sections typically 400 kilometers wide. Between ridge segments lies the active portion of the transform fault, where frequent earthquakes and mountain building expose mantle rocks at the surface. Transform boundaries on continents are relatively rare. The most famous active example is the San Andreas Fault, which separates the North American plate from the Pacific plate. This 2,300-kilometer fault ranks among the planet's most seismically active regions. The plates shift past each other at approximately 0.5 centimeter per year, generating earthquakes with magnitudes exceeding 6.0 roughly every 22 years. Advances in geodynamics, plate kinematics, and satellite geodesy allow scientists not only to predict Earth's future, but also to reconstruct its past. Reconstructions reveal paleogeodynamic settings and identify patterns in global environmental changes. Travel back 300 million years to the end of the Paleozoic era. The world looks vastly different. Before us stands a single unified supercontinent, Pangaea. Pangaea wasn't a uniform landmass, but rather several large continental blocks welded together by mountain systems. Stretching from polar latitudes to the equator along a meridional axis, Pangaea crossed all of Earth's climate zones. Near the end of its existence, Pangaea split into northern and southern continents, Laurasia and Gondwana. From Laurasia came modern Eurasia and North America. From Gondwana emerged Africa, South America, India, Australia, and Antarctica. Today, continents have reached nearly maximum separation. We live in a dispersed continental phase of Earth's long-term cycle. But what of the future? Multiple theories exist about how lithospheric plates will move over the coming hundreds of millions of years. Despite different names, Amasia, Pangaea, Ultima, Pangaea Proxima, all scenarios converge on one conclusion. Continents will reunite into another supercontinent in approximately 200 to 350 million years. This cyclical pattern of continental breakup and reassembly isn't coincidental. It's a fundamental process. Science cannot yet fully explain why this occurs, but evidence strongly links it to deep processes within Earth, particularly evolution of structures in the lower mantle. Earth has experienced at least 5 such supercontinent cycles throughout its history. Each cycle lasts 300 to 600 million years, during which all continental crust assembles into one giant landmass surrounded by a single vast ocean. Then rifting begins anew. The supercontinent fractures into several continental plates that internal forces drag across Earth's surface until they eventually reassemble. Will humanity survive to see the next supercontinent? That's debatable. But if we do, we'll face radical climate changes. If the landmass forms over the poles, ice will accumulate and persist far more easily, leading to extreme global cooling. However, any supercontinent configuration will trigger dramatic climate shifts. A single massive land area will completely restructure ocean currents, globally redistributing heat flows. Consider also that subduction of oceanic crust fuels volcanic activity. When a supercontinent forms, subduction largely ceases. We may view volcanic eruptions negatively, but they help maintain Earth's stable climate. Perhaps it's no coincidence that both the hottest and coldest periods of the past 350 million years occurred during Pangaea's existence. Earth in the distant future will bear no resemblance to the world we know. To predict continental drift, we must understand how mantle convection changes mantle composition itself. This knowledge improves understanding of earthquakes, volcanoes, ocean currents, greenhouse gases, and ice cover, all intimately connected to Earth's geology and deserving intensive study. Whatever form the next supercontinent takes, it will completely disregard the borders that humans with red-rimmed eyes painstakingly draw on maps, launching wars over these lands. Nature's power ultimately proves far mightier, having long demonstrated a supremacy beyond human control. Our planet's climate is extraordinary. No other known world possesses Earth's climatic conditions. Moreover, Earth's climate constantly changes. It's dynamic and variable. These changes stem from both human activity and, more significantly, the energy Earth receives from the sun, and how energy exchanges between different parts of what we call the climate system. Solar energy travels through space as radiation, short-wave solar radiation that reaches Earth regardless of orbital position or season. However, not all intercepted energy enters the climate system. Some reflects back to space through various processes, primarily via clouds and Earth's surface. Radiation not absorbed by the atmosphere reaches the surface, which heats up and emits its own long-wave infrared radiation. The atmosphere absorbs most of this radiation, then re-radiates it either back to the surface or upward into space. Overall, Earth maintains an average energy balance, though not uniformly across all locations or times. Nature, in its magnificent complexity and beauty, presents humanity with numerous climatic puzzles. Among the most fascinating is El Niño, a phenomenon significantly affecting weather conditions worldwide. El Niño describes unusual warming of surface waters in the eastern tropical Pacific Ocean. La Niña, its cold counterpart, describes unusual cooling of these same waters. Modern technology monitors this phenomenon through various instruments. The National Oceanic and Atmospheric Administration operates a network of scientific buoys measuring ocean and air temperature, currents, winds, and humidity. Approximately 70 buoys distributed across the tropical Pacific transmit data to researchers and forecasters globally. Combined with satellite imagery, these tools enable scientists to predict El Niño events more accurately and visualize their global development and impacts. The phenomenon influences ocean temperature, current speed and strength, coastal fisheries, and local weather from Australia to South America. El Niño events occur irregularly at intervals of 2 to 7 years, but aren't predictable like ocean tides. To understand El Niño, we must first understand normal Pacific Ocean conditions. Ordinarily, strong trade winds blow westward across the tropical Pacific. These winds push warm surface waters toward the western Pacific, where they border Asia and Australia. Due to these trade winds, sea level in Indonesia typically sits 0.5 meters higher, and water temperature runs 7 degrees Celsius warmer than in Ecuador. Westward movement of warm water causes colder water to rise toward the surface along the coasts of Ecuador, Peru, and Chile, a process called upwelling. Upwelling profoundly affects global climate. Warm water in the western Pacific increases rainfall around Indonesia and New Guinea. During El Niño, trade winds weaken along the equator. These changes in atmospheric pressure and wind speed shift warm surface waters eastward along the equator from the western Pacific to South America's northern coast. These warm waters deepen the thermocline, the ocean depth boundary separating warm surface water from colder deep water. During El Niño, the thermocline can sink to 152 meters depth. This thick, warm layer prevents normal upwelling. Without influx of nutrient-rich cold water, the eastern Pacific can no longer support its typically productive coastal ecosystem. Fish populations die or migrate. The World Meteorological Organization recently announced that the relatively cool La Niña climate phase has ended. A warm period is beginning, bringing severe drought to some regions and extreme precipitation and flooding to others. Annual reports provide key climate parameters: average annual temperature, pressure, precipitation, and phase states of major oceanic processes affecting planetary climate. The 2023 report indicated the cold La Niña phase, linked to the southern oscillation in the equatorial Pacific, would end mid-year. This particular La Niña lasted an anomalous 3 years instead of the usual 1 to 2. Energy accumulated in the global climate system and restrained by La Niña mechanisms could unleash with unpredictable force during 2024 to 2025. The previous temperature record occurred in 2016, also during an El Niño phase. There's a strong chance it will be broken in 2024. Climatologists predict with 60% probability that the next 5 years will be the hottest in meteorological observation history. Researchers forecast record heat globally, especially in the tropical zone between 30 degrees north and south latitudes, where over 1/3 of humanity lives. A temperature increase of 2.7 degrees Celsius by century's end is a realistic scenario, though worse outcomes with increases up to 4 degrees cannot be excluded. In such cases, up to 50% of the global population could find themselves outside favorable climatic niches, potentially triggering large-scale Earth surface transformation and fundamentally altering our planet's habitability. El Niño and other natural phenomena repeatedly demonstrate nature's captivating and sometimes dangerous power, significantly influencing global climate and weather. As scientific research continues revealing new complexities about El Niño and its relationship to climate change, more accurate models and forecasts will emerge. Advances in satellite technology and climate modeling already provide valuable predictions, helping us prepare for El Niño events. Preparation includes strategic water resource management, agricultural practices, and disaster risk reduction, ultimately contributing to global efforts adapting to changing climate conditions. Our understanding of Earth's fragile climate balance underscores our shared responsibility to preserve this equilibrium, at least for future generations. For adventure seekers and travelers, descending into Earth's interior might seem rather dull. Much of it consists of solid gray, green, and red rock, colors depending on predominant chemical elements. Earth's interior contains no fantastic caverns with dwarves, no giant worms, no submerged continents with abandoned cities. Extreme temperatures and immense pressure prevent the fanciful underground landscapes Jules Verne's imagination once created. Nevertheless, modern technology reveals that the subterranean world can impress us. From ocean trenches to Earth's ancient deposits, we'll descend into our planet's depths and reveal secrets lying beneath, using the latest data available. Our expedition employs an impressive array of investigation techniques: seismic exploration, measuring vibrations from earthquakes or artificial sources; gravimetric surveys, measuring gravitational force distribution; deep drilling, extracting samples from boreholes in Earth's crust; paleomagnetic methods, studying orientation of magnetized crystals in rock layers; astronomical and space methods based on meteorite studies; laboratory modeling reproducing and studying geological processes under controlled conditions; and paleontological surveys examining ancient fossilized remains of animals, plants, and mollusks. An impressive toolkit indeed. Let's gather our equipment and begin. The simplest way to penetrate Earth's depths is using existing boreholes. Many such holes exist, but the deepest is the Kola Super Deep Borehole, reaching 12,262 meters depth. For the record, no gateway to hell was discovered. While impressively deep, this borehole is surprisingly negligible compared to Earth's full depth. It penetrates approximately 1/3 of crustal thickness and represents just 0.2% of the distance to Earth's center. What did researchers find in the Kola Super Deep Borehole? First, they realized Earth's internal temperature map needed updating. They encountered temperatures far exceeding expectations. At 5 kilometers depth, temperatures exceeded 700 degrees Celsius. 2 kilometers deeper, temperatures reached 1,200 degrees. At 7 kilometers, one major discovery was the granite to basalt transition boundary. Another finding was liquid water existing much deeper than previously supposed. An unexpected result was the discovery of open fractures filled with salty water, evidence that Earth's crust isn't solid, but contains pathways allowing fluid flow. Even more exciting was discovering biological activity in rocks. At approximately 8 kilometers depth, researchers extracted a subsurface layer of marine sediments. These preserved 24 species of ancient plankton, over 2 billion years old. An envelope of organic compounds preserved these microorganisms virtually intact despite extreme pressure and temperature in surrounding rock. These fossils represent some of Earth's most ancient evidence of life. Remarkably, thousands of trillions of living organisms actually inhabit Earth's subsurface, many unknown to science. The record depth for sampling beneath land surfaces is about 5 kilometers. Beneath ocean floors, 10.5 kilometers. Moreover, up to 70% of all Earth's microbial species live underground. Several predominant types have been found beneath all continents. How these microbes spread through subsurface realms of all 5 continents remains unclear. Perhaps they migrate through the depths or penetrate from the surface through cracks in geological formations. These results suggest that even on our planet, enormous masses of subsurface organisms could exist without noticeable surface manifestations. This means there's no reason whatsoever to exclude life from virtually any solar system body, especially terrestrial planets. Having encountered ancient Earth creatures, we continue our rapid drilling. Before us lies the mantle, a thick layer of hot, solid rock between Earth's crust and molten iron core. The mantle consists primarily of silicates, a wide spectrum of compounds sharing silicon and oxygen structure. Common mantle silicates include garnet and perovskite. Another major rock type is magnesium oxide. Mantle temperatures vary dramatically from 1,000 degrees Celsius at the crustal boundary to 3,700 degrees at the core mantle boundary, so we won't encounter any plankton here. Viscosity also varies greatly. The mantle is mostly solid rock, but near tectonic plate boundaries, mantle rocks soften and can flow plastically over millions of years under great depth and pressure. Heat and material transfer in the mantle help shape Earth's landscape. Mantle activity drives plate tectonics, contributing to volcano and earthquake formation. The mantle divides into several layers: the upper mantle, transition zone, lower mantle, and D double prime zone, where the mantle meets the outer core. The upper mantle extends from the crust to about 410 kilometers depth. It's mainly solid, but more pliable areas facilitate tectonic activity. The transition zone lies between 410 and 660 kilometers beneath Earth's surface. Here, rocks undergo radical transformations. They don't melt or disintegrate. Instead, their crystalline structure experiences important changes, and rocks become much denser. Perhaps the transition zone's most important aspect is its water abundance. Surprisingly, crystals in this zone contain as much water as all Earth's surface oceans combined. But this water isn't water as we understand it, not liquid or vapor. Instead, water exists as hydroxide, a hydrogen and oxygen ion with negative charge. You couldn't brew tea with it. The mantle has never been directly explored, but many geologists study it by analyzing xenoliths, rocks enclosed within other rocks. Xenoliths providing the most mantle information are diamonds. Now the underground seems more appealing. Diamonds form in the upper mantle's unique conditions at depths of at least 150 kilometers below the surface. At greater depths and pressures, carbon crystallizes as graphite instead. Fortunately, we may not need to dig deep. Sometimes diamonds rise to the surface during explosive volcanic eruptions, forming kimberlite pipes through which one could wander for months seeking an exit. Through them, we can peer as deep as 700 kilometers beneath Earth's surface into the lower mantle. Research indicates deep mantle rocks are likely seafloor plates approximately 3 billion years old. Meanwhile, we reach the planet's core. Earth's core is the very hot, dense center of our world. The spherical core lies about 2,900 kilometers beneath the surface, with a radius of approximately 3,500 kilometers. Primary heat sources in the core include radioactive element decay, heat remaining from planetary formation, and heat released as the liquid outer core solidifies near its boundary with the inner core. Precious metals like gold, platinum, and cobalt also occur in the core. Tempting, but remember, we face a very hot journey. Another key core element is sulfur. In fact, 90% of Earth's sulfur resides in the core. Though we know the core is Earth's hottest part, determining its exact temperature is difficult. Core temperature depends on pressure, Earth's rotation, and elemental composition. Generally, temperature ranges from approximately 4,400 to 6,000 degrees Celsius. The inner core rotates differently than the rest of the planet. It rotates eastward like the surface, but slightly faster, completing an additional revolution approximately every 1,000 years. As Earth slowly cools, the inner core grows about 1 millimeter each year. It grows because portions of the liquid outer core freeze or crystallize. Inner core growth occurs unevenly, influenced by mantle activity. Growth concentrates around subduction zones where tectonic plates slide into the mantle thousands of kilometers above the core. Plates extract heat from the core and cool surrounding areas, increasing solidification events. The crystallization process is extremely slow, and continuous radioactive decay in Earth's interior slows it further. Complete core solidification would require approximately 91 billion years. Unsurprisingly, many geologists describe the outer core as Earth's geodynamo. For a planet to have a geodynamo, several conditions must exist. It must rotate, contain liquid in its interior, that liquid must conduct electricity, and it must have an internal energy source driving convection in the fluid. Variations in rotation, conductivity, and heat affect the geodynamo's magnetic field. Earth represents a Goldilocks case among solar system planets. It rotates stably at 1,675 kilometers per hour at the equator, creating spiral convection currents. Liquid iron in the outer core conducts electricity excellently, creating electric currents that drive the magnetic field. Energy driving outer core convection comes from liquid iron droplets freezing onto the solid inner core. Solidification releases thermal energy. Warmer fluids rise spirally, while colder solids sink under intense pressure. Thus, convection occurs. Our journey concludes. Hopefully it was interesting. We'll grab a couple of diamonds and return to the surface. Yes, our planet is unique in its natural wealth, biodiversity, vast oceans, continents, and stable climate. Its interior plays a crucial role in life's evolution on the planet. Earth science knowledge allows us to think globally and act locally, finding valuable resources like water, metals, industrial minerals, and energy, forecasting and preparing for natural disasters, and studying our own planet more than any other in the solar system. Examining Earth's history reveals wild environmental diversity and constantly changing climate. Dinosaurs thrived for over 160 million years with enormous potential. If we suppose dinosaurs survived, what factors might have influenced their development? The first serious obstacle would be climate change. Events known as the Paleocene thermal maximum, a geological event occurring approximately 55 million years ago, characterized by sharp global warming, significant atmospheric composition changes, and some species extinction. Global temperatures then rose 8 degrees Celsius above today's levels, and tropical forests covered much of the planet. In this greenhouse world with abundant vegetation, it's quite possible that sauropods, among the largest long-necked herbivorous dinosaurs, would have developed faster, reproduced at earlier ages, and increased their numbers more rapidly. An important feature of the late Cretaceous period was the flourishing of flowering plants, or angiosperms. During the Jurassic period, most plants were ferns and gymnosperms, typically less nutritious and harder to digest. Sauropods' enormous sizes likely resulted from the time and gut size needed to effectively digest such food. If plant evolution had continued as in our modern world, herbivorous dinosaurs would almost certainly have developed diets of flowering plants. Dinosaurs would find them easier to digest. We might expect an overall body size decrease, and giant Mesozoic dinosaurs would likely disappear. Oceans represent another enormous realm dinosaurs explored. Species like Spinosaurus had connections to river environments, while armored ankylosaurs often appear fossilized in marine deposits or lived along coastlines. Could Spinosaurs or ankylosaurs have followed the path of mammalian whales and completely transitioned to ocean living? Most likely, yes. Moreover, they might even return to land to lay eggs, or offspring could be born at sea, as with ichthyosaurs and plesiosaurs. Dinosaur diversity at sea would have spawned many terrifying legends. Together with that, it might have brought Lovecraft's emergence several centuries earlier. In any case, if they had survived to the present day, choosing swimming spots would require special care. Warnings not to swim past buoys would be more relevant than ever. Though remember, no buoys would help with survival. In the late Cretaceous, quite a few birds already existed. Unable to withstand competition, pterosaur diversity diminished. Only massive, fortunately toothless Ajdarchids remained, some with 12-meter wingspans. Possibly, humans would seem like amusing toys to occasionally play with against their will. Of course, researchers and paleontologists believe mammalian lineages were already developing before the extinction event. They had to deal with large, dangerous animals like saber-toothed tigers and even large antelope. These fellows had to handle various predatory dinosaur species, dromaeosaurs and oviraptors. But don't think a world with dinosaurs means constant bloody survival battles. For the most part, predators are widely distributed across terrain, and the world is relatively safe. If humans ultimately won this race, even if it took much longer, some dinosaurs would be domesticated. Others, especially large predators or those with beautiful plumage, would be exterminated. After all, humans have eliminated many mammoths, Mauritian dodos, moa birds, and other megafauna. Some would end up in reserves, while others would settle near humans like pigeons or rats. Other spheres of human life would change too. For example, since reptiles don't produce milk you can't buy at the supermarket, dairy products would be far less common. Culture would change from fashion to comic book heroes. Instead of Spider-Man, today's world would know Tyrannosaur Man, and ancient Egyptian gods would have heads of Saurolophus and Hadrosaurs. Some consequences are hard to imagine, and there's much to fantasize about. In this alternative timeline, perhaps some large herbivorous sauropods like huge Diplodocus and even carnivores resembling tyrannosaurs could have evolved in fascinating ways. The forces shaping our planet operate on timescales almost incomprehensible to human minds. Continents drift centimeters per year. Supercontinents form and break apart over hundreds of millions of years. Yet these patient, persistent forces have sculpted every landscape we know and will continue reshaping Earth long after humanity's chapter concludes. Understanding plate tectonics, climate systems, and Earth's internal structure isn't merely academic curiosity. This knowledge helps us locate vital resources, water, metals, minerals, and energy. It enables us to forecast and prepare for natural disasters. It reveals how profoundly interconnected Earth's systems are, from the deepest core to the highest atmosphere. We are temporary inhabitants of a dynamic planet that cares nothing for our borders, our timescales, or our ambitions. Nature's power infinitely exceeds our own. Yet, with knowledge comes responsibility. As we face climate change accelerated by human activity, as we witness species extinction and ecosystem collapse, we must remember, Earth will persist. It survived worse catastrophes than anything we can inflict. The question isn't whether Earth will endure, but whether we will, and what world we leave for those who follow. The same forces that built mountains, opened oceans, and cycled continents through billions of years of deep time will continue their patient work. Our choice is whether we live in harmony with these forces or futilely fight against them. The future is written in stone, quite literally, in the slow dance of tectonic plates. Our decisions today determine whether humanity reads that future as participants or as fossils.